Imagine one morning you bought porridge from your favorite vendor and the porridge was too hot for you to consume. In order to cool it, would you have added cold water directly to the porridge and then mixed it to cool it? No! You would rather sift that cup or rubber of hot porridge into another bowl of cold water to cool it. In the other sense, if the porridge was too cold for you, you would also sieve the porridge into hot water for the heat from that hot water to be transferred into your porridge. This is basically the idea behind any heat exchanger. Heat exchangers are devices that are used to transfer heat from one fluid to the other without the two fluids mixing. This is Group 29, and our presentation explores on a type of heat exchanger known as the fin tube heat exchanger. We shall be exploring its functions, its applications, its, ad- its advantages, and also how the first law of thermodynamics applies to it. Sit back and be informed. A background story on fin tube heat exchangers. Otto Happel, in collaboration with Professor Ludwig Pratt, is widely credited as the inventor of the fin tube heat exchanger, specifically pioneering the technology of the elliptical fin tube as a new air cooling device. First introduced in the early 20th century, fin tubes became widely used in the United States and Europe for industrial heating and cooling. Edward F. Moore was one of the early pioneers, patenting an improved fin tube heat exchanger in 1925. A picture of Professor Ludwig Pratt shown. What are fin tube heat exchangers and why use them? A fin tube heat exchanger is a device that transfers heat between two fluids, hence its name, heat exchanger. It has extended metal surfaces called fins, which are attached to tubes to help improve heat transfer. These, these heat exchangers are used in air conditioners, power plants, and car cooling systems. An image of the fin tube heat exchanger is shown, showing the inlet, the outlet, the direction of airflow, and also the tubed portion. Types of fin tube heat exchangers. Fin tube heat exchangers come in different designs and shapes based on their specific applications, including the rectangular, triangular, wavy, offset stream, perforated, and louvered. The plain fin tube is a simple design used in condensers and evaporators. The louvered fin tube also has small cuts to improve airflow and heat transfer. The perforated one also has tiny holes to reduce pressure drop and improve efficiency. The wavy one also has a curved shape that improves the mixing of air for better cooling. How do they work? From the diagram on the left, we observe that hot water enters the tubes. The heat from the hot water is transferred from the tube walls to the fins. The fins also have a large surface area, which enables the cold air that flows in to absorb the heat and to leave out as hot air. The large surface area of the fins help them to dissipate heat faster. Gradually, hot water heat from the hot water is taken out and then leaves as cold water. The fin tube heat exchanger is ideal for applications where a fluid has a significantly lower heat transfer coefficient than the other fluid. Materials used for making fin tube heat exchangers. The first material is copper. It is used because it is a good heat conductor and does not rust easily. Aluminium too is lightweight, cheap and durable, so makes it suitable. Stainless steel is also used because it is strong and lasts long, and is also good for harsh environments. Carbon steel is also less expensive but strong and is also commonly used. What engineers and manufacturers consider when designing a fin tube heat exchanger? They focus on optimizing for performance by improving efficiency through the following ways. 1. Using more fins to transfer heat faster, making the air move faster by using better fan designs, coating the fins to stop rust and improve performance, as well as adjusting airflow direction for better cooling. 2. Things they consider when designing. They also consider the tube size because the tube size affects how well the heat moves. They also consider the fin thickness in the material as it affects the efficiency. They also consider the speed of air and fluid movement. Applications of the fin tube heat exchanger. In the image provided, the radiator of an automobile such as a car makes use of the fin tube heat exchanger to cool the engine fluid. It has many small tubes with fins to transfer heat to the air. The air moves through the fins, removing heat from the engine. We should also note that they are not only applied in automobiles but also across industries. Air conditioners and heaters also make use of the fin tube heat exchanger to control temperature indoors. Power plants also manage heat from their steam and gas turbines, making use of the fin tube heat exchanger. Let us continue by discussing the advantages and potential setbacks of the fin tube heat exchanger. Advantages. They remove heat quickly because of their fins. They are small in size but work well. They are cheap for cooling and heating large spaces. They can last for a long time if maintained properly. While they offer remarkable efficiency, they can also bring about challenges that may lead to frustration. Dust and dirt can block the fins and reduce performance. They need regular cleaning and maintenance. When the fins are made of a high density, they can slow airflow, therefore increasing the pressure drop. Another focus of this presentation is to show how the first law of thermodynamics applies. It is simply stated as energy can neither be created nor destroyed, but can be transformed from one form to the other. It can also be stated as for all adiabatic processes between two specified states of a closed system, the net work done is the same regardless of the nature of the closed system and the details of the process. It is written as the sum of the heat transfer term plus a work term, which is equal to the mass flow rate multiplied by the sum of the specific enthalpy, kinetic energy per unit mass, and potential energy per unit mass due to its height. For the outlet minus that of the inlet. However, for a fin tube, the work term is negligible. Potential energy and kinetic energy are also assumed to be constant. Our equation therefore simplifies to heat transfer rate Q dot is equal to mass flow rate times enthalpy m dot times h for the outlet minus that of the inlet. Interpretation of our equation. From equation 2, the heat transferred equals the difference in enthalpy of the working fluid between the outlet and the inlet. The heat exchanger transfers energy in the form of heat between the fluids, changing their enthalpies. The fins also increase the surface area, enhancing heat transfer, and in other words, maximizing the heat transfer rate. If one of the fluids is air, which is usually the case, the fins compensate for the low heat capacity of air by improving the thermal conductivity. What is the thermodynamics equation used for? The thermodynamics equation is crucial for designing and analyzing fin tube heat exchangers because it quantifies heat transfer, ensuring efficient performance. The equation is used in the heat exchanger sizing. Engineers use this equation to determine the required surface area and fin design to achieve a specific heat transfer rate. The equation helps in selecting the right number of fins and tube materials for efficient energy transfer. The thermodynamics equation is useful in energy efficiency optimization. By knowing the enthalpy change, designers can minimize heat losses and maximize energy savings in industrial systems. This is essential in applications like boiler economizers, air-cooled condensers, and refrigeration units. The thermodynamics equation is also useful in performance analysis and troubleshooting. If the actual transfer heat rate deviates from expected values, it signals fouling, inefficiencies, or airflow issues, which draws the engineer's attention to errors early. Last but not least, the thermodynamics equation is useful for process control in chemical and power plants. It helps to ensure proper temperature regulation in steam condensers, reboilers, and heat recovery systems. It is also critical for maintaining safe and efficient operations. In this presentation, we explored the operation of the fin tube heat exchanger, its application in industry, advantages, and also how the first law of thermodynamics applies to it. We also discussed that choosing the right material and design of the fin tube heat exchanger to match the use makes it more effective. Future improvements include better coatings, new fin designs, and stronger materials. Let us imagine a world where every industrial process maximizes energy efficiency. A world where fin tube heat exchangers are at the forefront, transforming how industries consume energy and manage resources. As we embrace innovation and seek smarter solutions, let's reflect on how we can contribute to this vision. Every small improvement we make in our designs and processes can lead to significant changes in our energy consumption and environmental footprint. Thank you for your time and attention.